Now that you know in detail what are the port states, how to check what ports are open on the local machine, and how to scan ports on remote machines, I'll move ahead and talk about reject. Reject is another terminating target, and like drop, it denies the packet, but also sends back a reply packet to the source. By default, it replies with an ICMP port unreachable packet, and it's possible to specify the response packet using --reject -with option. Maybe you wonder why it's necessary to use reject when we have drop that silently drops any packet matched by the rule. And the answer is that sometimes it's more efficient to reject than drop packets, because dropping packets will cause TCP to retry the connection until the threshold for the retransmission is reached. The retransmission timeout is generally of tens of seconds. By rejecting packets, TCP aborts the connection, and the application gets to know that the connection has failed after just one round-trip time. Contrary to popular belief, drop does not give better security than reject. In this example, I reject forwarded or routed traffic that is going to port 69 UDP, and I inform the source by sending back an ICMP port unreachable packet. You can see the options of the reject target by running iptables -j reject -help. Let's try some examples. I want to reject SSH traffic from Linux 2 to Linux 1. This is Linux 2 and this is Linux 1. On Linux 1, I will add an iptables rule that rejects SSH traffic from Linux 2. iptables -a input -p TCP -d port 22 -s the IP address of Linux 2. -j reject. I don't specify any reject options because I want you to see the default option. On Linux 1, I'll start TCP dump, and I want to capture all the traffic from Linux 2. TCP dump, host, and the IP address of Linux 2. -n. Perfect. Now, on Linux 2, I'll scan port 22 on Linux 1 using nmap. nmap -p22 and the IP address of Linux 1. And we notice that nmap reports the port as being closed. And on Linux 1, in the TCP dump output, we can see those packets. I'm stopping TCP dump by pressing on Ctrl+C. Let's look for the packets. There are many packets, but let's take a look only at these two packets. Server 2, ending in 20, is sending a TCP packet with the SYN flag set to Linux 1, ending in 10. Here, this is the packet. The packet is dropped, and then Linux 1 is responding back with an ICMP packet to Linux 2. The ICMP packet is the default, which is port unreachable. And if I list the firewall, I'll see dropped packets. There is only one packet dropped by the rule. This packet. Now, I'll add the same iptables rule, but this time I'm using -i instead of -a. This rule will be the first rule in the chain and the rule that will match the packets. The previous rule will be deactivated because no packets will be ever been matched against it. And I want to specify what packet will be sent back to the source after dropping the incoming SSH packet. And I want a TCP reset. So --reject with TCP -reset. I'm starting TCP dump again. And I'm scanning port 22 again. The port is reported again as being closed. Let's take a look at TCP dump output. I'm stopping TCP dump. Let's look for the packets. These are the packets. We see how server 2 has sent a TCP packet with the SYN flag set, and in response, server 1 has sent to server 2 a TCP packet with the reset flag set. This is the response. Okay, one more check. I'll add this rule one more time, but this time I'm using the drop target instead of reject. This rule will be the first rule on the input chain, so it will match the packets. Drop. I'm starting TCP dump again and scanning Linux 1 again. Now the port is being reported as being filtered. That's because nothing is received from Linux 1. Let's take a look at the output of TCP dump. We can see that Linux 2 has sent SSH packets to Linux 1, which silently discarded the packets without responding back to the source. In fact, Linux 2 has sent 2 packets to Linux 1 and after that gave up entirely.